My name is Jeff Lestz. I'm a scientist at General Atomics, though some of this work was done while I was a postdoc at UC Irvine. Here's a very brief tour of my poster on the experimental comparison of ion cyclotron emission in the Lhd Stelerator and D3D Tokamak. The motivation for this work is that ion cyclotron emission, or ICE, is a collective instability that's being considered as a potential passive fast ion diagnostic for burning plasmas. So in this work, we performed a dedicated experiment on the Lhd Stelerator to better understand ICE and then compare back to previous observations on the D3D Tokamak. Three of the main results are that ICE is toroidally localized in Lhd, unlike in Tokamaks. This is a major difference. In Lhd, it appears that the edge electron density influences ICE more strongly than the Offmanik Mach number. And this large database we now have in Lhd on ICE reveals more complicated trends than were apparent in previous studies. As some additional background, ICE is a collective instability that occurs at energetic ion cyclotron harmonics, like you can see here. Despite the name, ICE is not Larmor radiation. We want to study ICE because it's observed very frequently in fusion plasmas. It's very easy to excite. And so it's been seen in the Lhd Stellarator, like in this figure, and it's also been seen in many different tokamaks, including D3D. But in order for ICE to be developed as a useful diagnostic, we must first improve our physics understanding. So we performed this dedicated experiment on Lhd to study the linear and nonlinear properties of ICE and how they depend on all these different plasma parameters. Here's a schematic of the Lhd Stellarator. You see there are tangential beams, and there are also perpendicular beams. These are the ones which drive ICE most strongly. And then there are high-frequency magnetic probes and RF antennas which can detect ICE. And since they're at different locations in the plasma, they can tell us something about where ICE exists in the device. This is one of the main results and differences, and that's that, unlike in tokamaks, ICE is toroidally localized near the active radial beam source in Lhd. So you can see that in this figure, where when we turn on one of the radial beams, beam number 4, then on the probe that's close to that beam, you see the ICE fluctuations right away, but you don't see them on a probe that's somewhere else in the device that's closer to beam number 5. But then when you turn beam 5 on, then you also see the fluctuations on that probe. So this is the localization that occurs in Lhd. But this is very different from ICE in tokamaks, because there, ICE appears with equal strength on all the probes around the device, no matter how close or far away they are from the beam. We can also infer the radial emission location of ICE by looking at the peak separation and then mapping that to the cyclotron frequency in the poloidal cross-section. And in Lhd, you see that ICE is emitted somewhere close to the edge. In D3D, the story is a bit different because it depends on whether you're in H mode or L mode. So when you're in H mode in D3D, it's similar to Lhd in that the ICE appears to be emitted near the plasma edge. But in L modes, the frequency maps closer to the axis. So usually, you detect ICE most strongly on the probe that's close to the beam that's turned on. But it turns out there are some cases in Lhd where even when the faraway beam is on, you can still detect a weaker ICE signal on this probe. And so you can see that here when the close beam is on versus the far beam is on. And so this is very interesting, and we want to understand if this is due to the fact that the particle orbits that are driving ICE may be localized, or maybe it has something to do with wave propagation. One plasma parameter that appears to affect the localization is the electron density. And so in our database, we found that for lower density plasmas, the ICE that you can detect on this probe when this beam is on, the faraway beam, is larger than it is when the density is larger. And so one thing that's different when the plasma density is higher is that the beam deposition is different. So here are two similar shots, except with different densities. And then this is the numerically calculated beam deposition profile. So this is like the beam density. And you see that for the higher density shot, there's a lower density at mid-radius because of the extra ionization at the edge. And so part of our ongoing investigation is whether the orbits of the fast ions born at mid-radius are responsible for the ICE that can actually make it around the device. There's also this interesting exceptional case at very low densities on Lhd where the tangential beams can drive ICE, and that ICE maps very deep into the core of the plasma, which is very different from the usual case, which is ICE driven by the radial beams emitted near the edge. And this is interesting to study because it appears that the core localized ice isn't really toroidally localized. It goes all the way around the device. And this is unlike the usual case of edge ice, which is observed most strongly close to the active beam source. So this may provide some clue about the localization mechanism. So on this slide, I show how the spectrum of ice depends on plasma parameters. And so one thing we found is that the strongest harmonic of ice tends to decrease in number as the authentic Mach number is increased. So it goes from number 3 to number 2, for instance. And this can be understood through linear theory, which depends on K-perp rho, which depends on the authentic Mach number times the frequency for ice. As far as the amplitude of ice, this appears to be most sensitive to the edge electron density in LHD, even more so than the authentic Mach number, which we can distinguish in our experiment because we varied the deuterium fraction in the plasma, which affects the mass density, which affects the Alfvén speed. One similarity of ice in D3D and LHD are that in both devices, ice tends to be stronger when the magnetic field is stronger. And so this is a similarity between the devices for this instability, but it's actually different than some other fast ion instabilities, which are typically stronger at lower fields due to larger authentic Mach number. And so with that, I'll just put up my summary and call out one conclusion, and that's that because there are some subtleties in this database, and there are some differences in how ice appears to behave in the Lhd Stellarator versus D3D Tokamak, I think this suggests caution when we extrapolate results between different magnetic configurations for ice. And so really this motivates us to use more advanced modeling, which incorporates full toroidal geometry. So hopefully we can understand why these magnetic configurations have different ice behavior. And again, the whole motivation for this work is that we need to improve our physics understanding of ice so that it can be leveraged as a fast ion diagnostic in the future. So this was a very brief overview of my poster, but if there's anything you're interested in more detail or just this work in general, I'd be very happy to talk to you. So please stop by my poster or reach out. And with that, I'll thank you for your attention.